Thank you. Yeah, hi everyone. Indeed, today I'm presenting PMEvo, our work on finding port mappings for out-of-order processors through evolutionary optimization. But first, let's have a look at processor architecture, because that's what we're looking into. Back in the day, processors used to follow at least roughly a structure like that. Instructions were loaded in program order, went through these pipeline stages sequentially one after the other, and executed in program order. We as programming language researchers naturally ask the question then, how can we use such an architecture most efficiently? And for this case, the answer is rather straightforward. We just need to make sure that we keep the pipeline full, so that we make sure that the instruction stream that we put in there has no hazards and the like. However, since these olden days, processes have become quite a lot more complicated. While instructions typically still are loaded in program order, they are then put into some decoder stage, which decomposes them into micro-ops. These micro-ops then are typically put through some complicated system leading up to a scheduler, which distributes them among execution units, so-called pods, which have the arithmetic and all these other execution units grouped behind them, and really can execute these instructions or the micro-ops out of order, so out of the program order, and potentially even in parallel. So with such a more modern out-of-order design, answering the question of how to use the architecture most efficiently becomes a lot more complicated. Because now we also need to make sure that we also have enough instructions available that are for which it is possible to execute them in parallel. Because not all instructions can be executed on every execution unit. And for this, we would need to know which instructions can actually be executed in parallel. This information is captured in what we call a port mapping. So a mapping from the instructions of the microarchitecture to the micro-ops into which they are decomposed, and from the micro-ops to the ports on which they can be executed. So you would like to have this information to understand how fast the program can be and also to make your code as efficient as possible. But the hardware manufacturers typically don't provide this information. It's typically a confidential information, which makes our lives, when we try to achieve peak performance, more difficult. Therefore, our goal is to infer such a port mapping, independently of what the hardware manufacturers say, from micro benchmarks and experiments. There has been previous work on that. They were mostly using hardware performance counters, which are these registers, dedicated registers in the CPU that you can configure to count special hardware events, like, for example, whether micro-ops are executed on some of the execution ports, which is really helpful for this task because it gives you quite a deep insight into the problem. So you can actually rather straightforwardly come up with experiments or micro benchmarks that you need to run and how to interpret these to find how the instructions are decomposed into micro-ops. However, not every CPU has these performance counters. Practically, you're mostly limited to Intel CPUs, and whereas x86 CPUs from AMD don't really have enough suitable performance counters, and if you're using some ARM architectures, you're even more lost. Therefore, our approach instead does not use hardware performance counters, but instead really relies on instruction throughput measurements. So really running experiments and more or less measuring the time that it is required to execute them. The benefit of that is that we can do that independently of the microarchitecture as long as we can measure the time required to execute our experiments. The downside is that we expect these results to be less precise because we have less insight into the hardware itself. And also, it's quite a lot more complicated to make sense of these results because the constraints are quite non-trivial. But still, it allows us to give at least some kind of information for the processes that are not supported by the other techniques. So now let's look into how the measured throughput and the port mapping that we want to infer are connected to each other. With a small example, let's assume we want to execute this experiment here, consisting of two add instructions, a multiplication instruction and a store instruction, assuming no data dependencies, and assuming that we want to execute them on a processor that executes instructions according to the port mapping that you can see here. For the sake of simplicity, we assume that each instruction is decomposed into just a single micro-op, which just makes the presentation here quite a lot easier. So yeah, when we want to execute such an experiment according to our port mapping model, the idea is that we have to distribute them to the ports, which are displayed here as these three buckets, according to what the port mapping allows. So one way of distributing this experiment would be this, where we have to put the mul and the store instructions into ports 1 and port 3 respectively, because that's the only places where the port mapping allows us to put them. Whereas the add instruction, we could place them either in port 2 or also in port 1. That's what is allowed here. So if you distribute this experiment for one instance of this experiment to these ports, we can see that we require 2 cycles because the maximal height in these buckets is 2. That's, however, not the throughput yet, because the throughput is talking about well, steady state behavior. If we, for example, add a second iteration of this experiment to the mix, we can achieve an execution that looks like this, where we actually take use of, or take advantage of the ability to put the add instruction to the other side. And in this case, we can actually do 2 instances of the experiment in 3 cycles. If we add more instances of the experiment to the mix, we are not getting any faster than that. So this really is our throughput, which means that we get 1.5 cycles per instance. And what we can see from this example is that, at least for this case where we don't have any data dependencies and the like, this throughput really directly corresponds to the port mapping. So if the port mapping would allow more things for the multiplication instruction, we could get a lower throughput. If it would have stronger constraints on the add instruction, we would have a larger number of cycles required. So really, there is a connection there that we can take advantage of to infer our port mappings. So from this rather intuitive explanation of how they're connected, what can we do computationally to really connect the port mapping and the throughput? The normal way of, the so far known and standard way of computing throughputs according to the port mapping model, if you know the port mapping, would be to encode the constraints as a linear program, not an integer linear program. So we actually can solve these with off-the-shelf solvers in polynomial worst case complexity. The other way that we propose in this paper is to use our nice bottleneck simulation algorithm, which has exponential worst case complexity, exponential in the number of ports. At first, that might sound bad, but as you can see from the graph, for a practical number of ports, which actually have risen since the PLDI 20 paper, so I had to adjust this slide a bit to the side. But still, we're in the area where we have at least, well, not quite 2 orders of magnitude faster execution times, but still close to that. So practically, this is a lot faster than using even a commercial LP solver for this problem. One thing worth mentioning, we have proven correct that this bottleneck simulation algorithm exactly models solving the linear program, which is quite nice, I think. So what we can do is we can measure the instruction throughput on the machine through micro-benchmarking and time measurements. And we have seen that we're also able to compute the instruction throughput for a given port mapping, the known one, rather fast. And what we want is a port mapping for the machine, so to which it executes. So in other words, we want to learn parameters for this nonlinear function that decides how instructions are executed on a machine, which is the port mapping, based on, which is basically input-output examples, micro-benchmarks with the measured throughputs. This quite obviously is a machine learning task to some extent. We decided to use an evolutionary algorithm for this instead of, well, whatever else you might use, like deep learning and the likes, because this one allows us to find a concise and interpretable representation, the port mapping itself, and not some neural network parameters that would be hard to interpret. And also, pretty nice thing about evolutionary algorithms is that we don't have to think about coming up with derivatives of the problem, which would be rather complicated, but instead we can just use our fast port mapping simulator for efficient fitness evaluations. So that's quite nice. Other approaches could be also feasible, but that's just the one that we found really helpful and really work. So that's the one that we went for. So let's look into what exactly we did with our evolutionary algorithm. On a high level, it follows this straightforward structure, which is really common to most evolutionary algorithms. We start by initializing some population of individuals randomly, so it's just some candidates for solving the problem. And then iteratively until some convergence criterion is achieved. So for us, it means that the fitness doesn't change anymore. We take individuals from the population, we recombine them to produce new offspring, we evaluate the fitness of this new offspring, and we select from the previous individuals and the new offspring, the new population, to maximize fitness. Let's look into all of these components in a bit more detail. For the population, an intuitive choice is just to have a collection of port mappings. So each individual is a randomly generated port mapping. In the beginning, they won't make much sense, obviously, because they're randomly generated. But throughout the optimization process, they will converge closer to the actual behavior of the machine. For our recombination operation, we use a binary recombination operator, which means we take two individuals from the population and produce from them two new offspring port mappings. And we do that on an instruction by instruction way. So we look for each instruction separately. We take all the micro-ops of both parent port mappings, throw them basically into a set, shuffle it, and randomly separate it for the new offspring port mappings. So for example, with for the null instruction for these two parent port mappings, one of them using micro-ops U1 and U2, and the other one U3 and U4, we might get offspring that looks like this. So in this case, both taking micro-ops from either parents' port mappings here. This just leads to mixing around these the port usages here, so that we can achieve try a lot of different things throughout the evolution. An important part clearly is the fitness goal, because it's or the fitness metric, because it determines what we're optimizing for. On the one hand, we would clearly like to minimize the average prediction error on some experiment set that should execute according to the port mapping model. If we have a low prediction error on that, we found an accurate port mapping that accurately models what the processor does, which would be nice. On the other hand, we also need practically another component in our fitness metric to minimize the complexity of the port mapping that we get, because the port mapping model is actually quite expressive, but it also allows for quite a lot of additional microbes, for example, that could be in the decomposition but not really affecting the throughput, which we would like to avoid in our explanation here, because it just blows up the port mapping and makes it less easy to interpret. But we can optimize for that, and then also obtain a compact port mapping representation. One key aspect of this clearly is, for the first part, how to choose an experiment set, because that really determines what we're optimizing for. We tried just randomly sampling dependency-free basic blocks and using them, but actually we found that in this case, the generalization behavior was not that good. So just randomly trying basic blocks or combinations of instructions basically wasn't really helping us that much here. So instead, we generate our experiments according to a fixed scheme, no randomization in here. The idea is that we, on the one hand, want to make sure that the experiments actually execute according to the port mapping, which means that we avoid any data dependencies in there, because if the throughput is determined by data dependencies, then we don't learn much about the port mapping. On the other hand, we also want to make sure that the experiments are able to really expose the characteristics of the port mapping. And for this purpose, the way that we went ahead is to look into, well, in the first benchmarking each instruction individually to get their throughput, but then also, depending on this measured throughput that we found, to combine pairs of these instructions at different ratios so that we can find out things like whether instructions are completely independent of each other, in which case hopefully only the maximum of the throughput would be achieved by combining them, or if they compete for the same bottleneck resource, in which case it's more like the sum of the throughputs that we would expect, or something in between, which might happen. Making sense of these experiments still, especially if you have micro-ops in there, is, if you're looking at it manually, still is quite complicated, but that's what our evolutionary algorithm is for, to make sense of that. Okay, so we implemented this in our tool, PMEvo, and we performed some evaluation. What we looked into was if we infer such a port mapping and use it to predict the throughput for dependency-free basic blocks, we randomly sampled them, how accurate can we get? We looked at 3 different microarchitectures. On the one hand, the Intel Skylake architecture, which was in scope for previous works. It's interesting to just compare against the other works that have more insight into the tools. And on the other hand, on the AMD Zen Plus architecture and also on the ARM A72 architecture, which were out of scope for previous works. So yeah, the tools that we compare against are, on the one hand, uops.info. That's a source of these port mappings that were inferred by hardware performance counters. Then Intel's architecture code analyzer, which by now is well, no longer officially supported, but still was state-of-the-art for quite a long time. They may use proprietary information. We don't really know what they're doing inside. Then we're also comparing against iThemal, which was, at least back then, a recent neural network-based throughput predictor. And then also LLVM-MCA, which is basically an open source replacement for Yaka using LLVM's scheduling models. The first 3 of these only apply to Intel. Yaka, obviously, uops.info because of the missing performance counters, and iThemal, they just used it only for the Intel platforms, so only for that models are available. LLVM-MCA does have some models for the other platforms based on the scheduling models. It's also worth mentioning that the comparison, again, with Yaka, iThemal, and LLVM-MCA is not entirely fair, because those are more general throughput estimators. So they are able to work with more general code, so they could also handle dependency-free code, or are even intended for that. But still, I think the comparison is interesting because it shows us what the state-of-the-art is with modeling these port mappings in these tools. So I present the evaluation results with these heat maps for each combination of approach and microarchitecture. I'll show one such heat map. This one is the heat map for PMEvo, so our learned port mapping, and the Intel Skylake architecture. We can see that, what we did is we randomly sampled 40,000 dependency-free basic blocks. We measured the time required to execute them on the actual hardware, and we looked what the predictions for the throughput were according to the tool. And each measurement we put into a bucket of this heat map that is further to the right, the higher the measured or the required number of cycles was to execute it, and further to the top, the higher the prediction in cycles was. Yeah, and darker buckets mean more experiments in there. We can see that here, for example, most of the experiments follow the diagonal line, which means that measured and predicted throughput line up pretty closely. For the other works, Info, Yaka, and LVMMCA, we see a somewhat similar picture, also mostly following closely the diagonal line, which is nice for our evaluation methodology, because we also need to make sure that our measurements make sense, really. The only odd thing that you might see are these clusters there underneath the diagonal line, which basically means that the measured number of cycles is larger than the predicted number of cycles. That might seem like, yeah, a measurement error. But actually, if you look into what these basic blocks look like, you find that basically all of them have bit test instructions that use memory. And if you look into the measurements performed by the Info people, you can get an explanation of what's going on there. Because for these bit test instructions, you can find that the throughput according to the port mapping here on the left in the TP column is, or so the required number of cycles, is considerably lower than the throughput according to the actual measurements. So they observed also that the execution is slower than what you would expect from the port usage itself. Together with the rather complex port usage that you can see on the rightmost column there, would assume that there are some kind of resource conflicts or dependencies among the ports that apparently the tools. So the tools were aware of the port usage, but not of the dependencies in there, which explains the underestimation there. PMEvo is not aware of this inconsistency and therefore just produces a port mapping that explains what can be seen from the throughputs. Slightly different picture for ITHEMO, because there we can actually see that the measurement accuracy is not on par, which is quite interesting because they do report high numbers in their paper. One possible explanation for that is that we're just looking at dependency-free code, whereas they trained and also evaluated their neural network on code that was emitted by a compiler for benchmarks, which means that we would expect there, for example, way more dependencies than in our code. But still, interesting data point to consider. For the other platforms, for AMD Zen Plus first, we can only compare against LVMMCA because, as I already said, the other tools don't support it. But we can see that the picture for PMEvo still looks somewhat similar to the Intel one, maybe slightly wider around the diagonal line, but still following it somewhat closely. Whereas on the LVMMCA side, we can see actually quite drastic overestimations here. Notice the difference in scale. So here, the state of the art was just not very accurate. And yeah, we can get a lot closer there with our approach. We get a similar and even more extreme picture for the ARM platform. Here, we can also see some kind of deterioration with PMEvo's results. We do have underestimations of the required cycles, which might be related to the, at least in comparison to the x86 architecture's slightly more simple out-of-order engine, which means that they probably don't follow that well to the port mapping model, and there might be other resource constraints in there. But if we compare it again to the LVMMCA model, we can see that there are even more dramatic overestimations in there. So also there, I think it's fair to say that we improved over their predictions there. Okay, so to summarize what we've seen, port mappings are quite important for really low-level performance prediction and finding out how to execute your code fast. Because the hardware manufacturers typically don't give you this information, we developed an evolutionary algorithm that is able to infer them. This was really made feasible through this nice bottleneck simulation algorithm that we've proven correct. And our evaluation shows that our results are close to on par for the previous work that had hardware performance counters for them, and could open up new architectures where previous works were just not applicable. thanks for the attention. Do you have questions? Okay.
Should I?
That would be the best.
Okay.
Thank you for the talk. I guess my question is like a more high-level question is like, how would you actually use this kind of information, say in a compiler, to like how do you make use of this kind of throughput information? Could you detail on that a bit?
Well, it's so the throughput. Well, the nice thing about our approach is that we don't only produce the throughput. So that's what we evaluated on, because that's really what we have. But we also have this interpretable representation of the port mapping, which basically tells you which instructions you can execute in parallel. Because if they're decomposed into microops that can be executed in parallel, then you see that. And yeah, LVM's backend, for example, has these huge table gen files, which, among other things, also take this port usage into account, and they're used for instruction scheduling. You can also use them for as component for other performance simulators. So there are other works that also use this port mapping internally, which also benefit from that.
Okay.
Is there no other questions?
Okay, let's thank the speaker.